let's start off with this. Okay, so an array of flip-flop facilitates to develop memory devices. An array of flip-flops can store binary information temporarily. Now, let's look at this. Okay, so these are assertion reason type questions. Okay, so what was your flip-flop? I think we've discussed about this previously. A flip-flop is basically a 1-bit memory cell, and a group of flip-flops together help you make a register. Okay, so a register helps you store these binary informations. Okay, so let's look at this. They say A is correct, but R is incorrect. A is incorrect, but R is correct. Both A and R are incorrect, and both A and R are correct. Okay, so let's look at this. Let's go through this. What is your flip-flop? Your flip-flop basically has two stable states. Okay, it's also called your bistable multivibrator. Okay, it's used to store state information. Next, let's look at this. Okay, so the circuit can be made to change your state signals to one or more control inputs and will have one or two outputs. Okay, so that's why you got two stable states coming in here. Next, it's like the basic storage element in your sequential logic. So sequential logic is basically where you take the output and feed it back into the input. Okay, so these are the uses of your flip-flops. Now, this is the main thing to remember. Flip-flop is a 1-bit memory cell and can be used to store digital data. Okay, so what do you do now? You just have 1 bit, right? So you group all these flip-flops together to make it a bigger group, so that you can make a bigger group of flip-flops, which is basically called your register. Okay, so if you have an n-bit register, what's going to happen is you can store basically n-bit words. Okay, n-bit words that can be inserted into it. So if you have a 4-bit register, you can insert 4 bits into it. Okay, so yeah, I think we discussed about this too, like just a second. Yeah, we discussed about this. I think we discussed about serial input, serial output, parallel input, parallel output, serial input, parallel output, and parallel input, serial output. Okay, so S is your serial and P is your parallel. So these were the different registers that we kind of like discussed. Okay, so this is what they kind of like saying. Your binary data in a register can be moved within the register from one flip-flop to another with these several methods that are there. Okay. Okay, so these are basically called shift registers. Okay, so they can allow you to transfer the data from one flip-flop to the other flip-flop inside this register. Okay, so now let's move on to this next question that we have. Okay, so these kind of circuits which have diodes in them, okay, these are basically called DTL. Okay, so this is called diode transistor logic. Okay, and these kind of circuits basically tell you about AND gates, OR gates, NAND gates. Okay, there are going to be some circuits which have transistors involved in them, but here we are looking at the case of a diode. Okay, so let's try and understand how to understand this circuit that we have here. Okay, so let's feed in input 0 to this. Okay, so if you feed in input 0, what's going to happen? So let me just write this. This is a minus, this is a plus, this is a minus, this is a plus, this is a plus, this is a minus. Okay, so this is 0, which is being input here. What happens here? This is forward biased. Okay, and if you input 0 here, this is also forward biased. In that case, what's going to happen? Okay, so let's just kind of like look at what type of gate this is. Okay, so let's look at the options first. You have an OR gate, NOR gate, AND gate, and NAND gate. So what you're supposed to do is feed all these inputs that are there. 0, 1, 0, 1, 0. Just a second. Okay, so 1, 0, 0, 1, 1, 1. Okay, so what you're supposed to do is basically feed all these inputs into this diode. See whether they are reverse biased or forward biased. Okay, And based on that, you get an open switch or closed switch. Okay, and this will help you understand whether there's going to be a V out coming here. Okay, so let's just go through it step by step now. Okay, so this is the OR gate, the DTL circuit for your OR gate. Okay, and this is the DTL for your AND gate. Okay, so you should notice this. The first thing that you should notice is this guy. Okay, it's in the normal direction flow of current. So why do they have the arrow in the diode? Basically, it's telling you which direction the current flows. So the current is flowing through this direction. Okay, and in this case, the current is flowing through the other direction. So the arrow basically points out which direction the current is flowing. Okay, so now let's look at this. I feed a 0 onto this. Okay, so what's going to come out here? Okay, a 0 is going to come out here. Okay, so this is basically positive and negative, positive and negative. So basically this is reverse biased, right? Okay, so let me just consider this 0 to be negative. Okay, low. 0 basically means low. 1 is basically your high. So this is basically a reverse bias diode. This too is reverse bias. So what's going to happen is you're going to get a V out as 0. Now, if you have a 1, what's going to happen here? Okay, so let me just put this. So this is a forward bias diode. That means there's going to be a current that's flowing through this, and there's going to be a V out that's coming out. So that's a 1. Okay, even though this guy is not on, this guy is on. Okay, so whenever you have on, whenever it's in the forward bias, it's on. So whenever it's on, there's going to be a current that's flowing through here, and then you're going to get an output voltage. Next, let's look at this. So you have a 1 and a 0. Okay, so let's just remove this out, and then you have a 1. Okay, so here you have a 0. Now let's look at this. So this guy is 1. This is in forward bias. This diode is on. That means there's a current flowing through this, and then there's a V out that you get. So that's 1. Now let's look at the state when both are 1. Okay, so when both are 1, both these are in forward bias, both of these are on. So then you end up getting a V out coming back here again. So you end up getting 1. Now, the AND gate is a little confusing because it's not as easy like this to understand. Okay, so let's go through it a little more slowly. Okay, so you have 0 here. Okay, so this is what? This is positive, this is negative. Okay, this is positive, this is negative. Okay, so you have a 0 here too. Now let's look at this. Okay, so you have an ES, you have an out, you have an RL. Okay, that's here. Now what's going to happen here? So you have a 0 here. Okay, you have a 0 here. Now because of that, what's happening here? This is a reverse bias, right? This is in forward bias. So there's going to be, both of these are going to act basically like an open circuit. Okay, okay, so that's the whole idea. So both of these are going to act like an open circuit. What happens then? So then you end up getting whatever input voltage that you had put in, you end up getting a V out. Okay, so whatever input voltage was there, that's going to come up here because both of these are in forward bias. Now let's look at this case. Okay, so this is 0 here, this is 1 here. So this is in forward bias. This is in reverse bias. Okay, so in that case, what's going to happen is this is not there. Okay, this is basically going to give you a 0, and whatever input voltage that you had given here is going to come out here. Okay, so now let's look at this case where you have 1 and 0. So what's going to happen here? You have a 1, you have a 0. This is going to be in the on state. Okay, wait. This is going to be in the off state. This is going to be in the on state. So whatever input voltage that you had given to in2 is going to come out here. Okay, so now let's move on to 1 and 1. Okay, so what's going to happen here? Basically, this is going to act like a closed circuit. In that case, what's going to happen is this current is going to flow through here and going to come out. So basically, you're going to be getting a 1 that's going to come out here. Okay, so if you have different input voltages, whichever one is higher is going to show up. Okay, that's not the case here. Both of them are same, or basically, let's say if you have something like 5 and 10. So if you have these two as your input voltages, whatever is higher is going to be showing up in the output. Okay, so let's just review this. Again, so OR gate using the diode logic. OR gate has 2 or more inputs and only one output. The output of the OR gate is high if one or more inputs are high. Okay, if all inputs are low, both the diode becomes in reverse bias and hence acts as an open switch. Hence the output voltage is 0 volts. Now, if A is high and B is low, the diode D1 becomes in forward bias and hence act as a closed switch, neglecting the diode forward resistance, and hence the output is high. Okay, now if A is low and B is high, the diode D2 becomes in the forward bias and acts as an open switch. Hence the output is high. And if both the input is high, then the output is equal to one or more of the positive values of input. That means if you have something like 5 and 10, your 10 value is going to be coming because it's a higher voltage. Okay. Now let's look at for your AND gate using the diode. So AND gate has 2 or more inputs and only one output. Okay. So the output of the logic AND is high if all the inputs are high. And for other inputs, it's low. So if your A is high and B is low, A and B are basically the inputs that I've given that. So basically it's in 1 and in 2. Okay. So the diode becomes in reverse bias. D1 becomes in reverse bias and hence acts as an open switch. Also the diode D2 becomes in forward bias and acts as a closed switch, hence the output is low. So whatever input that you have given passes through the one which is on, and that's what output you are going to be getting. Okay. So now let's look at this. If A is low and B is high, the diode D1 becomes in forward bias and acts as a closed switch. Also, the diode D2 becomes in reverse bias and acts as an open switch. Then your output is low. So if all the inputs are 0, then all diodes become in forward bias and acts as an open switch. Hence, the output is low. Okay, so when all the inputs are high, the diodes become in reverse bias and hence acts as an open switch. Hence, the output is high. So I've kind of like recapped whatever we've kind of like discussed before in these two slides. Okay, so I suggest you go through this AND gate a little more carefully, okay, because it's not as evident as your OR gate using diodes. Okay, so let's look at this. The bandwidth of your frequency response curve of your amplifier increases in positive feedback configuration, negative feedback configuration, CE configuration, and CB configuration. So what I want to talk about this is, let's compare it with an amplifier that is already there, okay? Not with the CE configuration and CB configuration, but I will kind of like, you can probably go through it. I'll put out the table over there, and you can kind of like go through all the properties of CB, CE, and CC. Okay, so common emitter, common base, common transistor are the different common emitter, common base, and common collector are the different configurations that you have in your transistor. So you can probably go through it. Okay, so this is basically the properties of your positive feedback circuit and negative feedback circuit. Okay, so in your positive feedback circuit, what's going to happen is the overall phase shift is 0 or 360 degrees. Now, in your negative feedback circuit, basically, it's going to be about 180 degrees. Okay, so that means if the input signal is like this, you're going to be getting an output signal that looks like this in your negative feedback. Okay, so there is this thing that positive feedback is basically used for oscillators, and negative feedback is used for amplifiers. Okay, so because when you have positive feedback, the instability in the circuit increases, whereas when you have negative feedback, the stability of the circuit is becoming better. Okay, so let's look at this. Your output voltage basically increases in positive feedback, whereas it decreases in negative feedback. Okay, the gain increases in positive feedback, whereas it decreases in negative feedback. Noise also increases, decreases. It's kind of evident because you know that the instability in the circuit in positive feedback increases. So it's kind of like evident from that point, all these things. Okay, so you can remember it using that particular term. Then the feedback and input signal is in phase in your positive feedback, whereas in negative feedback, it is out of phase. It's about 180 degree out of phase. And now the next important point that they've asked in the question is bandwidth. Okay, so the bandwidth basically decreases in positive feedback and increases in negative feedback. Okay, So this is the important point that you have to note, and that's what they actually kind of like asked you in the question. Okay, so the bandwidth of frequency response curve of the amplifier increases in positive feedback configuration, negative feedback configuration, CE configuration, or CB configuration. So basically, the bandwidth of the frequency response curve increases in the case of a negative feedback configuration. Now, in this case, let's look at your CE and CB and CE configuration. And basically what you're doing is you're comparing it with another amplifier, and they just mentioned configurations there. So I don't think you should probably look into those terminologies. You should probably just focus on positive feedback and negative feedback. That's the options that are given there. So the CB common base amplifier is known for a wider bandwidth. Okay, so common base. Okay, so you could probably remember it this way. Common base, B stands for your base, B also stands for the bandwidth. So you can remember that CB configuration has a wider bandwidth than the CE configuration. Okay, so let's look at this. Okay, so these are the different parameters that are there: input resistance, output resistance, voltage gain, current gain, power gain, and phase shift. Okay, so if you look at your CE, there is about a 180-degree phase shift. In your common base, there is no phase shift. Common collector, there is no phase shift. Okay, so you should probably go through all of this. Okay, I'm not going to be explaining this in detail because there are a lot of H parameters and things like that coming up. If required, and if I find questions on that, I will elaborate on this. So just go through all of these properties that are there. Okay, so let's look at this. Okay, so in a sequence of computations, the process is not a stable process. So I want you to be careful about this. Okay, what I want you to be careful about is this. Okay, not a stable process. That means it's an unstable process. Okay, so now what I'm going to do is I'm going to show you the definition of your stable process, and then we will come back to the options that are there. Okay, so the rate of accumulation of error decreases. The rate of accumulation of error decreases, but the relative rate of accumulation decreases. The rate of accumulation of error decreases and relative rate of accumulation of error increases. The process is not related to the relative accumulation of error. Okay, so let's look at this. Okay, so what do you mean by stable computation? Okay, so in a sequence of computations, the rate of accumulation of error decreases. Then ultimately the solution will be a good solution. So this is pretty logical. Okay, so if the rate of accumulation of error decreases, then the ultimate solution will be a good solution, and the process is called a stable process. Now, there's something else that's coming up. There is something called the relative accumulation error that's coming up. Okay, relative accumulation error. So if the rate of accumulation of error increases, but the rate of relative accumulation of error decreases, then also the process may be a stable process. Okay, but if the rate of relative accumulation of error also increases, then the process is unstable. Okay, so one thing that you have to note is you have rate of accumulation of error. Then you have relative error coming up. Okay, so rate of accumulation of error, then rate of accumulation of relative error. So here, what are they saying? They're saying if the rate of accumulation of error decreases, it is a stable process. Okay, it is a stable process if the rate of accumulation of error decreases. If the rate of accumulation of error increases, okay, if this increases, but the rate of accumulation of error decreases, then also the process may be stable. Okay, but if the rate of accumulation of error also increases, then the process is unstable. Okay, so what are we looking here at? We're looking at an unstable process, not a stable process. So the rate of accumulation of error decreases, but the rate of relative accumulation of error increases. So it's going to be option C. They're looking for the property of an unstable process. What I have given you is a stable process. Okay, the definition of a stable computation is what I've given to you. You have to invert the terminologies and then apply it over there. Okay, so let's move on to this. Okay, so this is a question that they give full marks for, because I think there is a little bit of ambiguity in like who kind of invented the BJT. Okay, so BJT, sorry, the FET, field effect transistors, because it was patented at a particular point of time. Okay, and it wasn't really made that time, but the idea was there. So the person who's patented it is given the credit for it rather than the person who actually made it. Okay. So yeah, so let's look at this. Okay, so now what you can immediately realize is the diode is something that came first. The microprocessor is something that came last. Okay, so do you see the diode here in the first? Okay, so you see the diode here, but the microprocessor is something that was invented, like a later point of time. So it's supposed to be coming last. So all these options are wrong, basically. Okay, so this is the order that I could find. I've kind of like switched this. Okay, so BJT was actually your BJT was your BJT is basically something that came before the FET. Okay, it was actually there practically, but the FET was patented before that. Okay, so by Julius Edgar Linfield. And the thing is that when you have these kind of inventions that are coming up, some people patented early. The idea was there before, but they never made it into practice, and some other people would try to make them into reality. So that's the whole point of giving this question. Is a little bit confusing. Not just confusing, it's kind of ridiculous, because there are a lot of people who get involved in making one kind of a particular device. And not just that, this is not something that's physics related. I mean, it's just something that you have to like memorize the year and things like that. But I think you can do it logically by just looking at which was the first device that was there. It was a diode. Which is the last device that was like the device that was invented at a later point of time, it's a microprocessor. So if you don't find those two options at the ends, then you know that the question is wrong. Okay, so they give full marks for this question at that point of time. So you can just go through all of these dates. Okay. So now let's look at your paper 3. We've come to the end of paper 2 for your 2014. We're going on to paper 3. Okay. So the Newton-Raphson formula is given by. Okay, so this is pretty simple. I think you might have done this in your numerical methods. So the basic idea is that you need to look at the slope. Okay, so let's just quickly derive this. Okay, just a quick figure. Okay, so let's look at this. Okay, so you're looking at the slope. Okay, here. So when you look at the slope, basically you're going to get opposite by adjacent. So let's look at this. You have an AB by AC. Okay, so that's your tan alpha. Now, this side is your function. This side is the value of the function, right? Your input value that you have. So now what are you going to do? You're going to find it at a particular point, f of xi, okay, minus some value that you have here. So that's probably taken as 0 here, okay? So then f prime, which your slope basically gives you the derivative of the function that you have, okay? So this slope is your f prime xi, okay? You've got an f of xi that's coming up here divided by this value that you have here. So you've got an xi minus xi plus 1. Now you need to kind of like alter this, okay, so that you get the next value of xi plus 1. So what you need to get is basically, so when you're looking at your Newton-Raphson method, the basic idea is you're looking at the slope at a point, okay? So this is a point, this is the slope that you're trying to calculate. Now the next idea is I want to calculate the slope at this point. Okay, so I need this next input to continue my calculations. So how do I find out the next input? I kind of like draw another line here, and then I get up something like this. Okay, so this is the next tangent that I have to find the slope at. And then after that, you kind of like reach this point. So then you end up finally coming to the value of the function where you have your xi equal to 0. Okay. So this is the basic derivation of that. So you have an xi plus 1 is equal to xi minus f of xi divided by f prime of xi. So even though you don't remember it, this is pretty simple. You can just derive it using the slope of the function that you have here. Okay, so let's go back. Let's look at this. So it's basically option B that you have. Okay, so your xi here is basically n. So you have an xn plus 1, xn minus f of xn divided by f prime of xn. Okay, so now this thing, I'd suggest you actually calculate the integral directly. Okay, so what you can do is when you're doing this, instead of using the Simpsons 1/3 rule, okay, if the options are quite far apart, you can just directly calculate this value and then you can get the answer. So you have an e power x once you integrate this, okay, then you have a minus 1 and 1. So you have an e power 1 minus of 1 divided by e power 1 because you have an e power minus 1 basically. So let me just expand that so that you don't get confused. You end up having an e minus 1 divided by e. Okay, so this is the value that you have actually without using the Simpsons 1/3 rule, but I will kind of like show both of the methods to you. Okay, so once you calculate this, you kind of like realize it's option B. Okay, so let's move on to this. So basically, instead of working it out using your Simpsons 1/3 rule, what you can do is you can evaluate this directly. I think I kind of like discussed this in the previous paper too. I think there you had a Simpsons, they just had given Simpsons rule, not 1/3 or 3/8, they just gave Simpsons rule. So you can just evaluate it out directly if it's a simple function. Okay, and this is basically a 1/3 rule. So let's just review this. You've got your h divided by 3, which is the interval. Okay, so it's 1/3. So this you can remember by just the name. Then you have a y0 plus yn. So you take the first point and last point. Then you have all the odd points that are there. So y1, y3, y5 that are there. Okay, 4 times those number of odd points, 2 times the even points that are there. Okay, so now let's look at this. Okay, so you assume that n is equal to 4. Okay, so I've kind of like assumed that n is equal to 4 here. So if you want a better value, you can just kind of like take more number of n values, more number of intervals that you want. Okay, so how do you calculate the size of each interval? H is equal to b minus a. That's basically my 1 minus of minus 1. So this is basically the 1 that you have here. Okay, this is basically a minus 1. So you have 1 minus of minus 1 divided by 4, which is equal to 0.5. Now, I kind of like drawing this table personally. So I'm going to write out all the x values that I have incremented by this 0.5. So if I do minus 1 plus 0.5, what am I going to get? I'm going to get a minus 0.5. So that's what I have here. Then if I add another 0.5, I end up getting a 0. If I add another 0.5, I end up getting a 0.5 and so on. So let's calculate, we basically calculate the value of your f of x here. Okay, so after you calculate the value of your f of x, you basically substitute for y0. Okay, so the important thing that you have to remember is this starts off with y0 and not y1. Okay, so many people make a mistake of starting it with y1 and ending it with y5. Then you have to alter this formula accordingly and you won't be able to get this even set and this odd set. So it's really confusing. So I bet it's best you start off with your y0 and then proceed further. Okay, so that's about the Simpsons 1/3 rule. Now let's look at this. Okay, so the error in your trapezoidal formula is of the order of, I think we discussed about the error bounds formula. So what is the error bounds formula basically giving you? It's looking at, okay, so let me just elaborate on this. You have some kind of a function x square, which kind of like represents the, let's say, represents the data points that are given to you. Now, if this is the set that you have, if this is the line that you've kind of like drawn, okay, if this is the data point that you have, the difference, the maximum difference is basically the error bound. Okay, so the maximum difference between the actual value and the true value, between the value of the function that you have approximated to and the true value of the point, is basically going to be giving you something called the error bound. Okay, we've discussed about this before, I think. Okay, so we're basically going to look at the error bounds formula for all of these trapezoidal, midpoint, and Simpsons, and then kind of like come to it. So I think you know this. I kind of like repeated this several times. The error bound is like h squared. Okay, so it's of the order of h squared. So let's look at this. Okay, so you're basically approximating this. Okay, so we kind of like discussed about all of this. Okay, so what does error bound tell you? It tells you about the maximum possible error in your approximation. Okay, so let's look at the error bound on your trapezoidal rule. So if you have the triple derivative of the function less than or equal to k, some particular value of k, and if x is between the range of a and k, then et is basically the error involved in the trapezoidal rule. So let's look at this. Basically, what do you have your h to be? H is equal to b minus a divided by n. So what do? I kind of like take one of this out. Okay, and I make this a square. So I end up getting k divided by 12 into b minus a into h square, right? So since your h is equal to b minus a divided by n, I end up getting this, okay? So let's look at this. What's the step size of this? H is equal to b minus a divided by n. Okay, so ES is less than or equal to K, which is b minus a into h squared divided by 12. So it's going to be of the order of, this should have been ET. Okay, I'll correct it and then I'll share it with you. ET, so ET is proportional to h squared. Okay, so that's what you've got in your question. Okay, so this is the midpoint rule error bounds. Okay, for your midpoint rule, then you have the trapezoidal rule, and then you have the Simpsons rule. This is what we kind of like did last time. So it's of the order of h power 4. Okay, so you pull out one b minus a and then you end up having something like this. Okay, so which of the following is not a tensor? Okay, so this one, I feel like this is not very good, okay, because the options that are given to you, and then they end up saying that it's mass. So, okay, with the options that are given to you, you kind of like say it is mass, but a tensor of rank 0 is a scalar, and mass is basically a tensor of rank 0, okay? So, I feel like the question wasn't very nice, okay? But you can like choose a value that is not a vector. So the thing here is that the gradient of a scalar field, I've always kind of like repeated this, gradient of a scalar field is a vector. Divergence of a vector is a scalar. Okay, so when you have a gradient of a scalar, okay, some function f, it is going to give a vector. And okay, so this dot should not be here when I'm writing the gradient. Okay, so this is not there. Then if I take this, if I write the divergence of some vector, say f, okay, this is a vector f, it's going to end up giving me a scalar. You can actually try it out too. Apply your del operator to this, let's say xi cap plus yj cap plus zk cap, you end up getting x plus y plus z, okay, or you end up getting 1 plus 1 plus 1, which is 3, and that's a scalar, okay, once you apply your del operator onto it. So I don't think this is a very nice question. You can't just say that mass is not a tensor. It's basically a tensor of rank 0. Okay, so that's what I can write. Tensor of rank 0 is your scalar. Vector is a tensor of rank 1. Okay, so these are the details of that. Okay, so now this is basically related to the difference, divided difference formula. Okay, so I think it's called the Newton-Gregory first difference or second difference and things like that. Okay, so these are the options that are given to you. Now this is a little bit of an ambiguity, and I don't think this was challenged during that time. Okay, so basically these two options should be correct. Okay, so this notation xs comma xt and xt comma xs, both of these should apply, because if you multiply a -1 on both sides, you end up getting the same thing. Okay, so I want to kind of like elaborate on that point that you have. Okay, so let's look at the table. So this is the Newton's divided difference table. Okay, and this is how you kind of like denote the differences. So you take this f of x1 minus f of x naught and divided by x1 minus x naught, and that's how you get your f of x naught. So let me just write that down. F of x naught comma x1 is equal to f of x1 minus f of x naught divided by x1 minus x naught. Okay, so this is what you have. Okay, so let's just look at some kind of a sample table that is given. So you take a 1 minus 0 divided by 1 minus 0. So let me just do the second one because the values are same here. So you have an 8 minus 1 divided by 2 minus 1. Okay, so this is how you're going to be doing your differences, and I'm sure you might have done it in BSc very well. Now the thing is that, okay, so when you write this down, so you write an f of x1 minus f of x naught divided by x1 minus x naught. So let's just multiply it with a negative sign on the top and the bottom. Okay, so you end up having f of x naught minus f of x1 divided by x naught minus x1. So what do you end up getting? You basically end up getting something like this. So if this is the way it's denoted, f of x naught comma x1 is going to be giving you this. then f of x1 comma x naught is going to be giving you this, but the only difference is that you multiply it with a negative sign in the numerator and denominator. Basically the value is going to be the same. So what do you have now? F of x naught comma x1 is equal to f of x1 comma x naught. Okay, so that's what you have. And if you look back at your if you look back to your options, you basically have an f of x s comma xt, which is equal to f of s minus f of t divided by xs minus xt. So if they wanted to like write it in the proper notation, they should have put an ft first, ft minus fs divided by xt minus xs, but they haven't done that either. So I think they should take these two options into account. This could have been challenged at that time, but I think nobody spoke about it. Okay, so I want you to be a little careful about this question because it is not very clearly written. Okay, so yeah, I will kind of like elaborate on it why. Now, which interpolation formula does not give any information regarding the error committed during approximation? Okay, so these are the different interpolation methods that you have. So what do you mean by interpolation? Basically what you're doing is, let's say you have some kind of set of data. Okay, so you have some population is a good thing. Okay, so you have kind of a set of data. Okay, so you basically have the population at 2001, 2002, and so on, like that, till about 2000, let's say 2020. Okay, so now what you do is basically you either extrapolate the data or interpolate the data so that you can find after so many years what was the population and look at what was the population so many years back. Okay, so if you want to find the population of 1995, you kind of like extrapolate the data, and if you want to find the population of like 2025, you kind of like interpolate the data. Okay, so this is the basic idea behind interpolation. And how do you do that? Basically you take some kind of a polynomial. Okay, just a second, polynomial, and what do? Let's say you have some kind of an x square that's there. Okay, so you have some kind of an x square function, and let's say that the data points are all over here and there and everywhere. Okay, so what you do is you kind of like try to fit it to this polynomial that you have. Okay, and you try to kind of like predict the value at some later point of time. Okay, so that's all to do with this interpolation. Okay, so what you're doing with interpolation is basically that. Okay, so this is basically a little bit of history on your interpolation. Okay, so what I want to focus on is the process of fitting a function through a given data is called interpolation. Okay, so this is the basic definition of your interpolation. You're fitting the data for a particular function. So you're taking the data points that you have and you're trying to make a function out of it. Basically something like that. Now you have your Newton's forward formulae, Newton's backward formulae, Lagrange's formula, and okay, so these are basically the ones that I would like to discuss here. Okay, and I would like to tell you why these two are not very nice to use. Like the errors for these two are not very practical to use, and this one is quite okay to use. Okay, so the answer is your Lagrange's interpolation, and I'll tell you why. Okay, so this is the error in your Newton's forward difference interpolation. So what are you basically doing? Okay, let's say this is your function that you have approximated it to. Okay, and these are the data points that you have. Okay, so some data points are going to come exactly as it is and the error is going to be minimal, whereas some data points are going to be a little bit different from your curve. So this difference is what we're basically looking at. Okay, this difference is what we're basically looking at. Just a second. Yeah. Okay, so this difference is what we're basically looking at. So what are you doing? You're basically taking the difference between the polynomial and your function, or your point at which the function is, or something like that. Okay, so let me just put it as y of x minus pn of x. Okay, so this is the polynomial that you have. Okay, and this is your y of x. Okay, that you have. So that's the whole idea there. Okay, so to find the error committed in replacing the function y of x by a polynomial pn of x, we kind of have to like subtract these two, and this is the error that you're going to be getting. Okay, so now we've taken a Newton's forward difference interpolation. That means the errors, basically your x naught value is going to be some kind of step value of h. Okay, so it's going to be basically equal spaces that are there. So you're going to get something like this. Okay, so this is basically your p value at that particular x. Okay, and then you kind of like subtract it because your x is equal to x naught plus ph. Okay, so you have an x minus x naught, which is equal to p into h. And here we're basically going to be finding step intervals. Okay, so you're going to be going it in steps in this range. From x naught to xn, you basically increment it by steps, and that step value is your h. Okay, so this is basically h power n, and then you have to kind of like compute the derivative of your, this is the power, this is the derivative. Okay, so it's h power n plus 1, whereas here it's n plus 1th derivative of the y polynomial. Okay, so that's what you're basically going to be getting, and this is your xi. Okay, so now what I will do is okay, so let's look at this and why it's not that very nice. Okay, so if you look at, just a second. Yeah, okay. So we do not have any information about this value that you have. So what you are looking at is basically the n plus 1th derivative of your function, and you do not have any value of this, and therefore you're basically like, this formula cannot be used practically. Okay, so that is the issue with your Newton's forward difference interpolation. Okay, so instead of that, what you do is you basically look at a Taylor series expansion. You don't have to know all this to kind of like look at the question, but I'm just telling you how to do it. You basically look at a Taylor series expansion, and then, okay, you end up getting something like this. Okay, so this is the formula that you have. Now I want to compare this Taylor series for all the other, for the Newton's forward difference and backward difference. You use the same thing effectively, but you just have a plus sign here. Okay, for backward difference, you end up having a plus. In the case of your forward difference, you end up having a minus. So if you look at this value, okay, so now what I'm going to do is I'm going to compare this Taylor's polynomial, which you use for your Newton's forward and backward differences, to the Lagrange's polynomial. Okay, the error that you get using this polynomial. So if you look at this, okay, so the information basically concentrates on x naught. Okay, but here what are you doing? You're splitting out the information at several points, x naught, x1, x2, and so on till about xn. Okay, so that's why this is a better thing that we have. Okay, so the error here is going to be extremely minimal. Okay, so now let's go and read the question. Okay, so here if you look at this, the idea is, which interpolation formula does not give any information regarding the error committed during your approximation? Okay, so basically I think what they mean is the minimal error formula. Okay, so that's basically a Lagrange's interpolation. So the question isn't very correctly framed, but there are going to be several questions that come up like this. Okay, so this is the whole idea about it. So the point that you have to remember here is, in case of the other Newton's forward and backward differences, this is what you're going to be using. You're going to be using the nth Taylor polynomial about x naught, concentrates on all the information at x naught. Okay, here you're using the information at particular distinct points, and you're going to be replacing those values rather than just taking this entire thing. Okay, so that's the whole difference between these two. Here you have it at particular points, you have the information directly. Here you have all the information concentrated at one point x naught. So the error is going to be like pretty huge compared to all of these. Okay, so yeah, so let's move on to this question. Okay, so I think we've kind of like elaborately discussed about groups. Okay, so the relation between two finite groups, many to one mapping, and so on. So we discussed about bijective and surjective and injective and all that. Okay, and we also discussed about homomorphism and isomorphism. So let's look at this. Okay, so I will just kind of like give you the definition. This is basically a many to one mapping. So in that case, it's going to be a homomorphism, right? Many to one is homomorphism. Okay, so let's look at this. Okay, so what is your automorphism? An automorphism is an isomorphism from a mathematical object onto itself. So if you look at an isomorphism, what is it? It's basically a homomorphism that is one to one and onto. Okay, so one to one as well as onto. That means every input that you have here has a particular input. I mean, every output that you have has a particular input. Okay, and it's 1 to 1. So there's going to be only one and only one value of your output for every input. Okay, we've discussed about this. If you don't remember it, go back and look at that particular lecture. Okay, so what do you mean by a monomorphism? Monomorphism is an injective homomorphism. It's not onto, it is 1 to 1, but it's not onto. Okay, so that's an injective homomorphism. So injective is basically 1 to 1, surjective is onto. Okay, next one that you have is homomorphism. Okay, so basically it is telling you how similar are two groups or two rings or any such algebraic structures that you have, how similar are these two groups. Okay, so that's what your homomorphism basically implies. Okay, what are you looking at? Your isomorphism. Basically your isomorphism is a homomorphism that is 1 to 1 and onto, injective as well as surjective. Okay, 1 to 1 is injective, onto is surjective. Basically it's both together is basically called as bijective. So we've kind of like reviewed through that very quickly. Okay, so now let's look at this. If the Lagrangian does not depend on time explicitly, the kinetic energy is a constant of the motion, the potential energy is a constant of the motion, the Hamiltonian is a constant of the motion, and the Hamiltonian cannot be a constant of the motion. So I want to kind of like tell you something called the Noethers Theorem. Okay, so basically the Noethers Theorem states this: if you have a continuous symmetry, then there is going to be a corresponding conserved quantity. Okay, so if you have a continuous symmetry, basically continuous symmetries, just a second, continuous symmetries basically end up giving you some conserved quantity. Okay, so that's the basic idea behind your Noethers theorem. Okay, so I just wanted to kind of like tell you what it is all about. Okay, so Noethers theorem states that for any symmetry in the Lagrangian, there exists a quantity that is conserved. Okay, so for example, if the Lagrangian does not depend on time, then there is a quantity which we call the energy that is conserved. Okay, so now let's kind of like look into this in depth. Okay, so I wanted to do this derivation earlier, but I kind of like didn't find the right amount of time. So I think I will kind of like explore on this a little bit more today. So if the Lagrangian does not explicitly depend on time, then the Hamiltonian does not explicitly depend on time, and h is a constant of the motion. Okay, so I will kind of like tell you how to derive this from this. Okay, how to derive this Lagrangian. We kind of like have done this. Okay, it's called the energy conservation principle, and we've kind of like done this in the second semester, I think. Okay, so if your h does not explicitly depend on time, your h is equal to h of t, then h is not a constant of the motion. Okay, if it does explicitly depend on time, then it is not a constant of the motion. Okay, so let's consider a closed system, a system that does not interact with the environment. Then we expect that the Lagrangian of the system does not depend on time explicitly. That is your dou L divided by dou T is equal to 0. So there's no problems with this. But it does not mean that dl divided by dt is equal to 0. Okay, so why is that? Basically, the Lagrangian is a function of your position, velocity, as well as time. Okay, so it does not mean that dl by dt is 0, because when you kind of like do this, you're supposed to be doing a dou q divided by dou t into dt and so on. Okay, so you basically end up getting dou L, sorry, this should have been, just erase this. Okay, so this should have been dou L by dou q into dou q divided by dou t, because all that it means, it's not explicitly dependent on time, but there is implicit time dependence on the position as well as velocity coordinates. So that is something that we're supposed to be very careful about. Okay, so there is implicit time dependence, but there is no explicit time dependence is what they're saying. So you end up getting things like this coming up. Okay, so this basically becomes a q double dot. Okay, so that's the whole idea behind this. So the Lagrangian is a function. You have a qj dot, and t. Okay, so basically you kind of like expand it. I kind of like did these two expansions for you, and you do have a dou L by dou t. What happens to this? Basically, if it's not a system, if it's in a closed environment, and if it does not explicitly depend on time, this term that you have here will become 0. So this term goes to 0. So the only thing that you have is these two terms. Okay, now let's kind of like use the Euler-Lagrange equation. Okay, so you use the Euler-Lagrange equation, you get a d by dt of dou L by dou Qj dot is equal to dou L by dou Qj. So what do you have here? You have a dou L by dou Qj here. So you substitute that value over here using the Euler-Lagrange equation. Okay, so you kind of get this. Now, how do you kind of like simplify this? Basically, let's work backwards. Okay, so this is the answer. This is a question that I have. Okay, so let me just do d by dt of Qj dot. Okay, and you have a dou L by dou Qj dot. Okay, so this was the first function. Now you need to take the derivative with respect to your second function. So you have a dou L Qj dot into dou d by dt of dou L by dou Qj dot. Okay, so that's basically what you have here. Okay, so this term is this term and this term is this term. So basically you're kind of like trying to integrate this, okay, to get this value and then kind of like write d by dt in front of it. Okay, so that part is done. Now what do you do? Since you have this term, you can bring this term to the other side, right? Okay, so let's forget about this now. Let's take this term and bring it here. Okay, let's take this term and bring it here. Okay, so that's what we're basically trying to do. And this is your constant and it is minus h for these. Basically, it's a convention that we have. Okay, so let's write this negative h. Okay, so now I think we kind of like have this famous formula that you have. You basically have a qj, pj. I don't know if you remember. This is a q dot j, and you have a p here, and you have a minus l. Something that I think we have kind of like used a lot. Okay, so now what you need to do is we need to show that it's a constant, right? So now here you have something like this. You have a dou L divided by dou Qj dot. Okay, so when you try to kind of like write this half m v squared, what you basically write is a half m q dot with a j squared. Now you try to kind of like take this derivative that you have, dou L by dou Qj, you end up getting 2 times this, okay? 2 times t is what you end up getting. And that's why you have a 2t here. So if you haven't like kind of like looked at this, go ahead and look back at your classical mechanics notes. This should be there in the first semester, okay? So you have a 2t minus t minus v, okay? And then you have a t plus v, which is e, okay? So this is the basic idea that we have. And what do we have with that? We basically get the Hamiltonian equal to the energy. Now, in this case, we basically find the Hamiltonian system is equal to the total energy of the system, and we conclude that the total energy is conserved. Now, the equality of the Hamiltonian and energy is only satisfied under 2 conditions. Okay, so these are very important to remember. Okay, so your potential V depends only on position and not velocity. Now, this does not apply. Okay, so this does not become 2t if you have your velocity coordinate. Velocity basically becoming a function of, your potential V becoming a function of the velocity q dot. Okay, so in that case, what's going to happen? This term that we have here is basically going to have a potential term coming into it, and you won't be able to write this 2t. Okay, so that's the whole point. Now the Lagrangian is equal to t minus v, and you were able to get this. So if the potential depends on the position and not the velocity, then you're going to be having issues. So you cannot equate your Hamiltonian and energy. Okay, so you can't just say Hamiltonian. What is the Hamiltonian? I kind of like hear this every time. Okay, people ask what is the Hamiltonian, and they kind of like just say it is it is the potential, it's the total energy. Okay, so people say it's not very nice to say that, because the Hamiltonian is only the total energy under particular conditions. Okay, the total energy of the system is the Hamiltonian only under particular conditions, when you have the potential depending only on the position and not the velocity. So I want to stress that out very clearly. Okay, next, what you have is the transformation rules connecting the Cartesian and generalized coordinates are independent of time. That is what we based on this whole thing, right? We looked at whether the Lagrangian was independent of time. There can be implicit dependence on time, but there cannot be explicit time dependence. Okay, so that's what we kind of like point out here. Okay, so if you have such a system, Basically, this is kind of like an example of this. Okay, so the latter condition is not met for example, a moving coordinate system, and in such systems, the Hamiltonian will not be equal to the total energy. So if it is dependent on time, like in the case of moving coordinate systems, the Hamiltonian is not the total energy. So these are the two conditions where you need to meet these two conditions in order to actually get the Hamiltonian equal to the energy. Okay, so basically what we're looking at here is, if the Lagrangian of a system does not explicitly depend on time, then the total energy of the system will be conserved. So I think that's the whole point that we were looking at. Okay, so there's going to be, in the last question, there are going to be some principles that we use from here. So I want you to kind of like remember this during that time. Okay, so if the Lagrangian does not depend on time explicitly, the kinetic energy is a constant of the motion, the potential energy is a constant of the motion, the Hamiltonian is a constant of the motion, the Hamiltonian cannot be a constant of the motion. So let's just look at this carefully. If the Lagrangian does not explicitly depend on time, then the Hamiltonian is equal to the total energy, and the Hamiltonian is a constant of the motion because it is equal to the total energy. So that's the whole idea. This is the option C. Okay, so let's move on to the 9th question. Okay, so I think I kind of like told you what you mean by canonically conjugate variables. Okay, so if it is given to you that P and Q, I want you to remember your Poisson bracket here. So if it is canonically conjugate, your PQ is equal to 1. And if Q and P are canonically conjugate, PQ, capital P is equal to 1. Okay, so these are the whole ideas that we have. Okay, so this is the important trick that you have to use, rather than kind of like trying to find the transformations and there all those equations. The idea that you're supposed to use is this. Okay, so let's just review what are Poisson brackets and things like that. Okay, so let's look at this question. For the given transformation T1, Q is equal to P, P is equal to minus Q, and T2, you have Q is equal to P, P is equal to Q. These are the two transformations that you have, T1 and T2, where P and Q are canonically conjugate variables. Which of the following statements are true? So both T1 and T2 are canonically conjugate. Only T1 is canonical, only T2 is canonical, neither of them are canonical. Okay, so let's look at this. The Poisson bracket is defined by A, B. So you have dou A divided by dou Q and dou B divided by dou P minus dou A divided by dou P and dou B divided by dou Q. So let's just calculate what is Q and P. So this is basically 1. This is 1 minus 0 into 0. So you end up getting a 1. Okay, so that's your Poisson bracket for your Q and P. Then what do you have? You have, it's given that you have a P and Q. Okay, so the transformation is canonical if your capital Q, capital P is equal to 1. So what do? You substitute the capital Q and capital P, and you kind of like get 1 for the first transformation. So T1 is canonical, but T2, that you kind of like realize after you calculate this, it's not canonical. So this is equal to is not there. Okay, so T2 is not canonical. So this is what you get. T1 is canonical, T2 is not canonical. So it's going to be option B. Okay, so that's only T1 is canonical is the answer. So let's move on to the last question. This involves the principles that I talked about in the question 8. Okay, so if you have confusion regarding this, go back and refer question 8. Okay, so I'll kind of like write that down. Refer Q8. Okay, so Q8 in paper 3. Be a little more careful about that. Okay. So for conservative systems where the coordinate transformation is independent of time, the Hamiltonian function represents. We kind of like discussed about this just now. Okay, when is your Hamiltonian equal to the energy? The two conditions under which it is equal to the energy is if the potential energy does not contain velocity coordinates. Also, we discussed about this, it's coordinate transformations. Okay, the Cartesian coordinate transformations to the general transformations. Basically, it should not be dependent on time. So under those two conditions, your Hamiltonian represents the total energy of the system. Okay, so the Hamiltonian system is equal to the total energy if and only when, and we consider this total energy is conserved when these two conditions are satisfied. What did we say? We said that the potential energy V depends on position and not velocity. The transformation rules connecting Cartesian and generalized coordinates are independent of time. So these are the two conditions that we have. Okay, so this is what they're basically talking about there. Okay, so I think, yeah, we are done with this session.